What if machines could understand space the way humans do, not as flat images, but as living, continuous 3D environments? Volumetric intelligence represents that shift. Instead of only detecting objects, we model the world as volumes, capturing geometry, motion, and uncertainty in every part of space. Traditional vision systems are built around predefined categories: cars, pedestrians, bicycles. But roads and the real world don't follow categories. Debris, fallen trees, overturned vehicles. The long tail of rare objects is infinite. Object-centric models often simply fail to detect them, and what they miss can still cause collisions. Occupancy perception instead asks a safer question: is this space occupied or not? Bird's-eye view networks flatten the world, compressing the vertical z-axis. That simplification removes crucial structure. A hanging branch and a patch on the road become indistinguishable, even though one is harmless and the other is catastrophic. 3D occupancy restores that missing dimension, so height and safety return to the model. Here's the inversion. We stop asking, what object is this? We first ask, is this volume occupied? Once geometry is correct, semantics can refine behavior instead of driving decisions. This makes perception fundamentally more robust to unknown objects and irregular shapes. LiDAR and vision historically evolved in different camps, but both arrived at the same idea. LiDAR provides precise geometry. Vision infers depth from texture, motion, and perspective. Both ultimately converge on the same representation: a dense, volumetric model of space. LiDAR doesn't see everything. It samples points sparsely, leaving gaps everywhere. Modern LiDAR occupancy networks complete those gaps, inferring missing voxels based on context and prior structure. Diffusion-based models can even hallucinate plausible geometry in occluded regions, while preserving uncertainty, a powerful tool for safety-critical systems. Vision-only occupancy is exploding because cameras are inexpensive and already everywhere. The challenge is depth ambiguity. How do we lift pixels into physical space? Today's methods combine geometry priors, temporal fusion, learned depth maps, and transformers, turning 2D imagery into usable 3D voxel grids. Three dominant strategies structure vision-based occupancy. Depth-based lifting predicts depth for each pixel. Transformer queries sample features directly from images into 3D. Implicit fields treat occupancy as a continuous function, trained with differentiable rendering. Each trades accuracy, compute, and supervision differently, and research is rapidly converging across them. No sensor is perfect. LiDAR gives geometry. Cameras give semantics. Radar survives fog and rain. The strongest systems fuse them at the feature level, building unified 3D representations where each sensor reinforces the others. The result is perception that remains trustworthy even in adversarial conditions. Perception tells us what is here right now. 4D world models ask something more powerful: what will happen next? By modeling voxel dynamics over time, systems anticipate occluded vehicles, predict pedestrian intent, and reason about motion, not reactively, but proactively. Volumetric intelligence is becoming a universal tool for spatial understanding. Inside vehicles, it detects sleeping infants or dangerous passenger postures. In smart buildings, it enables presence-aware energy systems without tracking faces or identities. The same mathematics scales from highways to hospitals to classrooms. Traditional video analytics identifies people. Occupancy perception instead models anonymous volumes, posture, shape, and movement without biometric identity. That means we gain spatial awareness while preserving privacy, an increasingly critical requirement for real-world deployment. Voxel grids are massive, millions of cells, updated every frame. Sparse convolution, octrees, and channel-to-height tricks help, but compute remains a core challenge. Ground truth is another. Nobody can label millions of voxels by hand. Auto-labeling pipelines, simulation, and self-supervision are rapidly closing that gap and opening scalable deployment pathways. Occupancy networks see geometry, but recognizing what something is remains difficult when it was never seen in training. Vision language models bridge that gap. By aligning voxel features with language, systems can recognize new objects from description, moving perception toward true open-world capability. From autonomous vehicles to smart buildings, hospitals, and cities, volumetric perception is quietly becoming the foundation of intelligent environments. Safer roads, more efficient spaces, technology that respects privacy while increasing awareness. As these systems learn to model space, motion, and uncertainty, we unlock machines that adapt, not just react. And that brings us closer to a world where AI and humans coexist more safely, more intelligently, and more seamlessly than ever before. If this topic inspired you, dive deeper into the papers, experiment with the models, and share your insights. The next breakthrough in volumetric intelligence might come from you.